last class talking we talked quite a bit about the design project. So the only thing to say about that today is today's the last time to sign up for a specific team. I've been approached by a number of different groups that want to work as a group of 3. We'll have one group of 3. So if you sign up and want to be a group of 3, you'll kind of be entered into a random thing, and I guess not necessarily random, but I'll figure out who the group of 3 is. So we'll figure out one group of 3, but if you sign up as a group of 3, you may or may not get that choice. If you sign up as a group of 2, you should be good. Yeah, so today is the last day to do that. So after class, relatively shortly, figure out if you're going to do that. Otherwise, you'll magically end up in a group, and I'll let everybody know later today. The other thing to talk about, well, I'll talk about it in a little bit, I guess. Some things on the homework. Okay, I think that's all the announcement type stuff. So we finished last time talking about turbulent flow. Just briefly, I guess, when we should expect to see turbulent flow versus laminar flow, right? And turbulent flow is going to be where we get mixing and swirling and vortexes, and it's a lot of randomness. So it becomes very difficult to model. We have to use a combination of models and experiment and kind of cross-check our modeling results with what's actually happening in the real world in order to make sure we're accurately describing what's really happening. Thankfully, for a lot of common situations, people have already done that. So you're cross-checking stuff with previous experiments and maybe similar conditions that you might see. The key factors that are going to be dictating whether something is laminar versus turbulent is the relative importance of an inertia versus viscosity. So that's where we get what we call the Reynolds number. So, right, we talked about this last time, but make a big box yet again around the Reynolds number, because this is probably the most important. If you're looking at a flow, this is like the thing that you really have to know. What is the Reynolds number? What flow regime are we in? Are we in the laminar flow? Are we in turbulent flow? Right, so just to reiterate what all of these things are, rho is density, V is average, velocity, L is the characteristic length, right, which is this kind of nebulous parameter that it's kind of hard to define, but it changes for a given situation. So if you're working on, say, aerodynamics of like a car rear view mirror, the characteristic length is going to be like the size of that rear view mirror, maybe the dimension in the direction of the flow. If you're working in pipe flow, it's going to be the diameter of the pipe. If you're working, looking at a golf ball, it's going to be the diameter of a golf ball. So it's going to be something characteristic to that specific system. And without knowing kind of what that system is, it's hard to really define what that length is going to be. But what basically this does is going to be the most important length for this particular problem or situation. So generally, if you're flowing inside of something, it's the dimension that you're inside of. If you're flowing around something, then it's generally like the size of that thing. Okay, so those are kind of the two general as you can make it. It's the size inside, like a diameter or a width or something like that, or it's the size of the object if you're flowing around it. And then mu, of course, is just viscosity. Okay, this ratio of inertial versus viscous forces. we said, okay, for pipe flow, Reynolds number greater than about 2300 is turbulent. For channel flow, Reynolds number greater than about 1500 is turbulent. Just to kind of get it for flow along a flat plate, Reynolds number greater than about 10 to the 5. Okay, so there's no set number for every system. It's going to be dependent on the specific system. So flow along a flat plate, that would be like when we looked at the St. Joe River, like flow along that dam surface. That flow switches from laminar to turbulent at a Reynolds number of about 10 to the 5. Where L would be the characteristic length would be like the distance along the dam. So it's going to be some number. The one general thing that you can say is like a higher Reynolds number is going to be more turbulent. So there's some level of like degrees with this, where if you're at 2200, it's not going to be like you're perfectly laminar all the time. If you're at 2300 or 2400, you're always turbulent. There is some gray in this. You're going to be, if you're around 2300, you might have a situation kind of like the flow that we watched in the video, where you switch back and forth sometimes, and you can sometimes be laminar and then something will happen and there's a little disturbance and you flip turbulent for a little bit. So if you're right kind of at the border, you can have, like you can end up going back and forth. But if you're at 10,000 in a pipe, you're going to be turbulent. And you can be fairly sure of that, unless you're super, super careful at removing all possible disturbances, right? So, so these are kind of not hard and fast things, but they're general rules. So if we think about the video of the draining tank, we've watched it a couple times, so I won't pull it up now. If we just think about what's happening, right? Just so that's this system here where we have this tank draining. Hopefully with that little sketch, you remember what we're talking about. If we think about what's happening here, initially we start turbulent. We start with high Reynolds number. So our flow is turbulent. That's where, it's cloudy. We can't see through it because of all the mixing that's happening in the fluid. But as our pressure decreases, so delta P decreases as the tank drains. Right, that level is going to go down. So what happens because of that, our flow slows, and we have a transition to laminar flow. Okay, so we go from our flow slows, that means the Reynolds number goes down because the velocity goes down, and we flip from turbulent to laminar. So laminar flow has less friction, And we'll talk a little bit more about why that is. But if we have less friction, that means for the same pressure difference, we're going to get a faster flow. So we have, this is when we see it flip to laminar, we see all of a sudden the flow shoots out farther, so the velocity increases. And then as the velocity increases, okay, higher velocity means a higher Reynolds number. So Reynolds number goes up. So the flow flips back to turbulent. So this happens, and so you repeat that for a while, okay? So you're turbulent, that means you have more friction, so the flow slows down, which means the Reynolds number goes down, and all of a sudden, bam, you flip back to laminar. But then you speed up, and then, okay, then there's some little disturbance, and that flips everything back turbulent. The flow slows down again, low Reynolds number, and it flips back to turbulent again. So or it flips back to laminar. So that's why we get this like switching back and forth. And even, it takes a while before we fully switch to laminar and then we stay there, right? So it takes a while till we're kind of basically, if you want to think of it, we're bouncing around right around this border. Like we go a little bit below 2300 and then we get to laminar, and then we shoot above 2300 and then we're turbulent, and we're kind of bouncing back and forth right around this Reynolds number, which is why we see it flipping back and forth. Okay. So I want to give us a second way that we can think about some of these flows with regards to what are the forces that are acting in them. So far, we've looked at flows, and we've calculated velocity distributions and stuff kind of directly from the Navier-Stokes equation, which if you think about where that came from, that was essentially from, like, we drew a free body diagram basically around a little cube of fluid and did a force balance around that cube of fluid, right? So we did that on this, like, the most generalized thing possible. And we said there are forces in three directions, and it's this cube, and we got the whole big Navier-Stokes equation. And then we started from that equation and kind of pared it down to a simplified equation that we could solve. The other way to think about that, so we can think about like developing the Navier-Stokes equation as a force balance on a little piece of fluid. We can also think about it like the flip side is we start from a piece of fluid and do a force balance on that piece of fluid and use that on like a simplified geometry and use that to develop an equation. So the first question on the homework, I don't know if, I bet some people have looked at it and most have not, which is fine. But if you look at the first question on the homework, I'll just pull it up here for a second. Not that. Okay, the homework, again, if you haven't looked at it, that's fine. Here in part A, you're going to essentially be redoing what we did in class for flow between parallel plates. Right, so there was that Navier-Stokes handout, and we calculated what the velocity profile would look like for flow between parallel plates. We're going to be redoing that, but for flow in a pipe. You all are going to be redoing that. For part B asks, and I'll just underline this part. Do that. Look in chapter 8.3. So part B, and really for part A too, a lot of the answers to A and B are in the book. So, right, like people have already solved this before. You're not the first people, which is good, because if you're the first ones to ever try to solve this, that would be really hard. So I guess I care less about that. But what I want to try to get across with actually having you work through this is the Navier-Stokes equation. It's not just some big scary equation that comes from nowhere. Like it comes from force balances. And I think we have, as engineers, you do force balances on stuff all the time. And like, you know, there's a force acting this way and a force acting this way and what's happening. So I want to try to get us thinking about some of, like, where does some of this stuff come from in those terms, because I think they're more familiar to us. So part B asks, rather than considering like this big ugly differential equation, crossing terms out to get down to a simple differential equation, we're going to start and build our differential equation by looking at a force balance on a piece of fluid. So what that's going to look like, and we'll use this here to talk a little bit about the differences between a little bit about turbulent flow. But if we think of flow in a pipe, okay, so here's our pipe. Our flow, we can think about it as like a ring you redraw that. So there's a ring of fluid like this. So this is going to have a length here, which is dx. It has a radius, which is the radius, r. Our pipe has a radius here of whatever the radius of that pipe is, capital R. And the thickness of this ring of fluid here is dr. Okay. So rather than doing a force balance on some arbitrary like cube of fluid, we're going to kind of look at the geometry of our system and do a force balance on something that kind of matches the geometry of our system. And if we think of what a force balance would look like on this system, we're going to have flow. I'll give us some dimensions here. So this is the R dimension. We'll call that the X dimension or the Z dimension or whatever, down the pipe. We know just from kind of thinking about the problem that this is going to be a relatively good representation of the system. So we're going to have flow going, our flow is going to be going down the pipe, and it's going to be fastest in the middle and slowest at the edges, right? So there's going to be a change in the flow as you go from the center to the edges in the R direction. There's not going to be a change in the flow as we go like left to right. That's going to be essentially the same. And there's not going to be a change in the flow as we go around the circle. At any given radius, if you go around, the flow is going to be the same. So if you imagine like you're at the pipe wall, everywhere at the pipe wall around that whole circle, the velocity is 0. If you're 1 centimeter from the pipe wall, if you're 1 centimeter anywhere in that circle, your velocity is going to be the same. It doesn't matter where you are on that ring. So for that reason, this is a good control volume for this particular system. Because basically we can think of changing that radius R and looking at all the way at the very teeny tiny center, expanding it all the way to the edges of the system as we changed that, the radius of that system. And that's going to capture where our velocity is changing, because it's only changing in that dimension. So if we looked at this piece of fluid and we did a force balance, we would ask ourselves, what are the forces pushing and pulling on this piece of fluid. So there's pressure pushing on the kind of that ring all around the outside. So the force from pressure is pushing on that side. There's also a force from pressure pushing on that side. So at one side and the other side, there's forces from pressure. If you want to look at how did we handle this, look back at the note packet where we derived the Navier-Stokes equation. We did exactly this. The other thing that's happening, there's going to be a shear stress on the inside and a shear stress on the outside. So if you think it's going to be fastest in the center, so the fluid inside of our ring is going to be going fast, and the fluid outside of the ring is going to be going relatively slower. So we're going to have a shear stress inside of the ring kind of trying, right? The fluid's going faster inside, so that's going to tend to drag us along in the positive X direction. The fluid outside is going to be going a little bit slower. So the outside is going to kind of hold us back a little bit because that fluid's going slower. So there's going to be friction holding the flow back. So if we're at steady state, pressure balances with shear. So basically, pressure is going to be pushing us one way and shear force is going to be pushing us the other way. Basically, this is another way of saying that all forces are going to be balanced, right? If you're at steady state, these forces are going to be balanced. So you're going to have a system where you can kind of add up the forces and they're all going to be equal to 0. So if we look at again, you'll go through this in more detail than I'm going to right now. The book goes through it in more detail, so you'll kind of hopefully follow along the book unless you really want to make it up all by yourself, which I guess is fine too. But you can get the shear stress, tau Rx, is going to be equal to R over 2 dp dx plus C1 over R. Okay. Our boundary condition for this tau Rx evaluated at R equals 0 can't be infinite. So the shear stress at the center is going to be something that's not infinity. If you plugged in 0 for R in this equation up top, this second term here blows up. So this tells us that C1 must be equal to 0. And our shear stress, tau Rx, is equal to R over 2 dp dx. So what this tells us, this equation, and again, you'll flesh out some of this later, but this tells us that the shear stress changes linearly with R. So for pipe flow, the shear stress is going to be changing linearly with R. Tau equals 0 at R equals 0. Or the center and okay, so tau is going to be 0 at the center and maximized at the walls. When you all do this, you're going to be thinking about this in terms of laminar flow, and you'll use some of this same stuff to come up with the equation for what the flow looks like in laminar flow. But we didn't actually have to assume laminar flow or turbulent flow. So in laminar flow, we can say, aha, we know something about tau. We know Newton's law of viscosity. So that's fairly simple. So in laminar flow, right, this is in our homework problem. We know that tau Rx would be equal to mu du dr. Right, this equation here is just Newton's law of viscosity. Right, this is how shear stress and viscosity and velocity, these are how these all play together. In turbulent flow, there's no simple relationship. So if we think about turbulent flow, what this is going to look like, we have here velocity, or u, and here we have time. And what we saw happen when we looked at the video, we saw essentially a constant pressure. So there's a constant force pushing water down the pipe. But what we saw was kind of a flickering of the velocity, right? You guys remember that? Let's pull up the video just to show ourselves one more time. Let's see if we can. No. Come on, buddy. Just do that one. That one. Do it. Watch it. Ta-da. I can do simple computer things. Maybe. Come on, buddy. Yay. Right, so what we see is a very slowly changing pressure, or like force that's acting, but we see the velocity is shaking a little bit, like it's flickering. Right, if you look at the bottom, it's going up and down a little bit, it's changing. So what that means is it's changing velocity, not a lot, and it's kind of, you know, shaking up and down around the same kind of average value. But at any given instant, it's it's still shifting and moving. Okay, and then it switches total flow regimes, and other things are happening. But turbulent flow is kind of characterized by this flickering. So there's not a straightforward relationship between, like, say, pressure difference and how much friction we have, because the friction is basically always changing a little bit. And that's what I mean by there's not a simple relationship between, like, the shear stress, which is friction, and velocity, like, because velocity is always kind of like, it's characterized by kind of shaking around some average value. So we see that as something like this. So we would see the velocity over time doing something like that, where it's shaking around some sort of average value there. We have really then two different things that we can talk about. We can talk about what we call U bar, which is the average velocity. Or we could talk about this. This is the instantaneous velocity, the velocity at any given instant that we look at it. And then you can talk about the instantaneous velocity being made up from U bar, the average, plus this fluctuating component, right? We're bouncing around up and down around some average. So we can talk about it as a function of the average velocity, and I'll try to zoom in and draw it like that difference there. This is what we would call U prime, which is the fluctuating fluctuating component of the velocity. Okay, so if we think of turbulent flow, we have these two separate parts. What's happening kind of in average, but then also what's happening with the fluctuating component. So for turbulent flow, tau, well, let's consider this just for a simplification. So in a 2D turbulent flow, we're not going to consider all three dimensions, but just 2D, we could write something like this. Tau is equal to mu du bar dy, would be tau yx. So it's going to be, this relationship is still going to hold in the average. But then there's also this second part, which is going to be related to some of these, to this fluctuating component. So minus rho u prime v prime with a bar over top. So this is of u prime v prime, where u prime is the x component, the fluctuating component in x, v prime is the fluctuating component in y. This first part is just like Newton's law of viscosity. This is the viscous stress. The part that is related to viscosity, this is the turbulent stress. So there's shear that's related to kind of what's happening in the aggregate and average over long times, but then there's also shear stress that's happening because of the fluctuating velocity components. These fluctuations are essentially random, which is why we see the overall shear stress changing over time and the velocity basically changing over time. Okay, if we take this and look at tau yx divided by rho, this would be equal to mu over rho du bar dy minus u prime, the average of u prime v prime. This gives us this component. So tau divided by rho has units of meters squared per second squared. And this, what we call u star, is equal to the square root of that, where u star is what we call the friction. The friction velocity. It's a characteristic velocity of kind of this fluctuating component. Okay, so we'll look a little bit at what happens to this and where. So our friction, our shear stress, is made up of these two components. There's the viscous term and the fluctuating term. If we think about what's happening near the wall, okay, so near the wall we have the no-slip condition. So we know near the wall our velocities go to 0. Right? So at the wall, tau over rho is equal to mu over rho du bar dy minus u prime v prime bar. But at the wall, the total velocity is set to 0, so that means this fluctuating component also goes to 0 because the total thing is 0. So these those components die off. So what this tells us is that at the wall we have our shear stress just looks like normal laminar flow, right? We have just, this is just Newton's law of viscosity. So the shear stress, this fluctuating component, kind of the turbulence part of it, the mixing and going crazy, that part dies away when you get right next to a wall. And even when you're just like a tiny bit away from it, that part is still the u prime, v prime, the fluctuating part, the mixing, the randomness, that part dies away. And you have what we call a viscous sublayer. So there's basically this thin layer, like no matter what's happening in the broader fluid, it's mixing, it's going crazy. Right near the wall, because of the no slip, you have this region that looks basically laminar. So we have forms. So we see that because now it's just dictated by basically the change in the average velocity. So it looks essentially laminar. If we looked at okay, kind of combining what we just did, this thing that didn't really feel like why did we just do that with this other thing? We can look a little bit at what that looks like and say that near the wall, we can look at this equation and say that tau over rho equals mu over rho du bar dy. So this that characterizes the near the wall region. That is this friction velocity squared. Right, that's kind of how we define that. So we can say that the friction velocity u star squared equals mu over rho du bar dy. And then we can solve this, split it up and solve it as an integral. So du bar equals u star squared rho over mu dy, or well, which solves to u bar is u star squared rho over mu times y. So we get this kind of weird result that we have a linear velocity at the wall. We can rewrite this kind of the more common way to write it and why we defined this u star. U bar over u star. So the ratio is equal to u star rho over mu y. Which the right-hand side should look a little bit like something familiar, essentially the Reynolds number. The left-hand side is the ratio of these two velocities. So we can say something interesting. The velocity, second. In increase is linear in this viscous sublayer. So for turbulent flow, there's this region where viscosity wins, the no slip condition wins. In that region, we have a linear velocity profile. So we can tell, again, with some of the same types of modeling that we did for laminar flow, we can use that to try to understand what's happening right near walls in turbulent flow. Theo, you had a question?
Yeah, what was the y dimension? Is that the line effect?
This would be like, So the X dimension would be along the surface, the Y dimension would be just above the surface. We're so close to whatever the surface is that there's not really, like, it doesn't matter if the surface is curved or if it's flat. So this holds for pipe flow or for flow along a flat surface or wherever, because you're in like the flat earth limit. Your pipe might be curved, but you're really, really close to the surface. So this kind of works regardless.
So like the shearing is in the X and the Y is
Mm-hmm.
normal.
Yeah. So this would be, again, to just draw out like a quick picture. So you have some surface down here, and that's the X, that's the Y. And you have a viscous sublayer where basically your flow looks like this. Well, let me draw it like this. So basically your flow looks like this in this viscous sublayer. So you have turbulence up here, and there's kind of a fuzzy line between those, but you have this viscous sublayer where things are kind of orderly and well behaved. This increases linearly, and the slope of U bar over U star equals U star rho over mu. So this is kind of governing what happens like in this really close to the wall regime. As soon as you get a little ways away from the wall, okay, now in turbulent flow, then this fluctuation, and if we go back to what's happening with the shear, right when we get a little ways away from the wall, then this term starts to blow up and become dominant. So we have kind of two regions, one close to the wall and one a little ways away from the wall. Near the wall, things are still orderly. We can still come up with models like this that describe, what's happening in this region. Things work out pretty smoothly mathematically. And then we get a little ways away from the wall, and then things are going random and going crazy, and our math kind of breaks. So away from the wall, velocity fluctuations are going to be what dominate. And we'll get into next time, how do we talk about, or how do we model what's happening with velocity? We end up kind of totally throwing aside analytical models like this because they can't work because our velocity is random. So we end up going basically totally from analytical models, we have to go all the way to empirical models or semi-empirical models. They still have some basis in some of these things, but we have to throw up our hands a little bit and just say kind of what's happening on the average and do more like, fitting with random constants and fun stuff like that. So we'll talk about that next time. This time, I guess just my last admonition, read section 8.3 in your book while you're working on the homework. I don't expect you to be an expert in this, but hopefully this helps you kind of get at least a sense of where some of these equations and stuff come from as you work through it. All right, happy Wednesday. We'll see you guys on Wednesday. Right? Big break. So enjoy Easter break. Have a happy Easter, everybody.
I have a question. For the transfer moment, how do you know it's turn it in? Like, should we turn in our